So once again, welcome back and Happy New Year. So we were continuing data structures, non-linear data structures to be specific, and we've completed the height balanced trees example. So just to quickly revise, we started non-linear data structures, and in that we have seen trees, different types of trees. So binary tree, binary search tree, types of binary trees also, strictly binary tree, complete binary tree, and so we had seen how we can traverse a binary tree in order, pre-order, post-order traversals. Then we had gone for the different types of trees, and in that we have seen height balance and weight balance trees. So we started with height balance trees, where we have discussed AVL tree. AVL tree contains one value at a node, only one value, single value at a node. So if we want to store multiple values in a single node, then we moved on, we moved towards M-way search tree. And in M-way search tree, when we impose some constraints on minimum and maximum number of values and pointers, we have B trees. Now, if we only take internal nodes as a key and external node or the terminal nodes as data, then it was B plus tree, right? So all those types of trees we have seen, which were height balanced trees, and that we have completed. At the end, we discussed 2-3 trees, which is nothing but the B tree, but it has a special name because of having minimum and maximum constraint 2 and 3, right? So that's what we have covered till now. Moving forward, we want to have a look at weight balance tree today. So weight balance tree is going to be a binary tree again. Okay. So in weight balance tree, we'll say we are going to cover a binary tree which is balanced based on a weight associated with your data. Okay, now that weight can be anything, can be the number of occurrences, can be the probability, can be the distance, or anything that depends on the application, right? But what we do is the highest weight, which is having more importance, we are going to keep it to at the root or nearer to root. Okay, so that the highest weight, highest probability node will be much nearer to root, or will be at a place of root, and that can be easily accessible, right? That's the reason. So which simply says that the nodes which are likely to be searched or accessed have the lowest search time because it is nearer to root. And the best example to understand this thing is the Huffman tree, Huffman coding and Huffman tree. So with this example, we are going to understand what weight balance trees are and how it benefits us, right? So let's go and have an understanding part of how or what Huffman coding is. So Huffman coding is nothing but simple statistical coding. Look, it is not encryption, it is encoding, just changing the data in one form to another form. Okay. So in Huffman coding, what we do is, or why we do is, let's understand. Look, when we have a message and we want to transfer that message from one system to another system, okay, then that message, if we consider that is a text message, then it'll have number of characters. Now, not all characters occur with the same frequency in a statement, but still, when we want to transfer that message, we transfer those characters. And when we transfer those characters, all characters, if we are transferring it as a ASCII data, then one character will take 1 byte, right? Whether it is A or X, A to X, entire ABCD. All the characters are allocated same amount of space. And that's what the normal um, data transfer we consider. If we transfer our data in a simple text form, then this is what happens. So if you are transferring entire statement, A comes only once, then it will take 1 byte. E comes 5 times, then also E as a single character takes 1 byte. So if there are 5E, it will take 5 byte. So the size of your entire message doesn't depend on what number of times any character occurs. So the number of characters will be equal to the number of bytes you will require. Now that's what happens. But is there any way of saving your number of bytes, or the size, if we consider the frequency of our characters, right? Is there any way? Now that was the question, and the answer is Huffman code. So code word length, if we define and if we create some code words based on the frequency of character occurred, then it will be somewhat smaller or longer. It will not be the fixed size like ASCII value, right? So that is gonna help us, and if we define these code words, then we can take the benefit of this part, because length varies based from shorter to longer based on the frequency of character. So let's see how we can define code word for every character. Now this is the normal or basic algorithm of Huffman code, how you can define Huffman code. So to define a Huffman code, first thing first, we need to scan our entire message or the statement, okay, and find out what are the characters and what is the what are the number of occurrences of all those characters. So first step, list out unique characters in your message and also count the number of occurrences for all those characters. Now once you have that list, you sort it or prioritize it. All the characters you need to prioritize based on the occurrences, number of occurrences. So we are going to sort it in ascending order based on the occurrence. And once we have it, then we are going to create a Huffman tree. We are going to create Huffman code tree based on the priority list. Now how to create this tree, we will see it in further steps. So right now you simply understand that we need to create Huffman tree. Now once we have that tree, then what we do is we are going to traverse that tree, and when we traverse, we are going to define a code word. So from root up to leaf node, we are going to traverse that tree. And when we traverse, as long as it is a binary tree, we are going to go either left or right. So based on left and right, we are going to define code word with 0 and 1. And that's how we will define that code word. Now once we have a code word for each character, then we are going to apply that code word in the message. So again, we will we will scan our entire text and will replace those characters with the Huffman codes. Now this is the process. Step number 1, scan your entire text, find out unique characters and occurrences. Step number 2, sort or prioritize those characters based on the occurrence. Step number 3, create your Huffman tree. Once you have a tree, step number 4, traverse your tree and define your code words. once you have your code words, step number 5, replace each character with its corresponding code word. Now this is the process. So let's go and apply this process with one example and understand how everything happens. So let's take this statement. Area is seen near lake. Now we want to consider this as a message, and we want to transfer this message to another system, let's say. So what Huffman code says, you scan your entire text, list all the characters. So when you when you scan this entire text, these are the unique characters you will have. Capital E, small e, R, I, SP is space, okay? Space, then Y, S, N, A, L, K, and last one is dot. These are the unique characters you will find in your entire statement. Now, alongside that one, what you do is you calculate the number of occurrences for each and every character. So capital E occurs only once. Okay. Small e, now we need to calculate those. So 1, 2, 3, 4, 5, 6, 7, and 8 times small e occurs. Right? So likewise, you need to calculate the number of occurrences for all the characters. R occurs 2 times, and so on. So what are the characters present, and what is the frequency of each character? So when you calculate those frequencies, this will be your frequencies, like this one. 1, 8, 2, 1 space is 4 times, 1, 2, 2, 2, 1, 1, and 1. So I have that table here. Okay. Now this is the table we have calculated, and that's our step number 1. Now then step number 2, it says you sort or prioritize all your characters. Now to do that, what we'll do is we are going to use a priority queue here. Priority queue. And that queue will contain a node of binary tree, because after this step, in step number 3, we are going to create binary tree, Huffman tree. So for that, we are going to create each and every character as a data of binary tree node. And that node will contain the number of occurrence also. So we are going to create a binary tree node with character and a frequency. So character and a frequency. Now this is a binary tree node, remember. All these are binary tree nodes. Now once we create those binary tree nodes, what we'll do is we are going to place it in a priority queue. And this priority queue considers lower the occurrence, higher the priority. Remember, this is the thing. Lower the occurrence, it will have higher priority, so it is gonna be at the front. Lower occurrences will be at front, and higher occurrence will be at last. Okay, and this is what you should remember here. This is how we are going to consider a priority queue. In a while, you will understand why we are doing this thing, because higher the occurrence, we want to keep it on top in the tree, whereas lower the occurrence, we are going to keep it at lowest place, bottom place in a tree. Fine. So this is our step number 3. Then comes step number this was step number 2, and then comes step number 3. Create your binary or Huffman tree. So now let's understand how we can create Huffman tree here. Okay. So to create a Huffman tree, we already have a priority queue. Now what we are going to do is we will create a new node, that becomes a root, and then we are going to dequeue 2 times from our priority queue. So we'll dequeue 2 times. First dequeue operation, we will have one node, and that becomes a left subtree or a left child. And second dequeue operation will give you one node, and that becomes the right child. So this becomes binary tree. So we have created new node. Its left child is first dequeue operation. Its right child is second dequeue operation. And whatever the result we have, whatever the tree we have, what we're gonna do is whatever left and right child node has occurrences, we are going to sum it up, and the answer will be the frequency of newly created node. Okay, left child ka occurrence plus right child ka occurrence, whatever answer you have, that becomes the occurrence of your newly created node. Fine. And then this resulting tree we are going to enqueue back in our priority queue. वो आंसर के साथ हम उसको फिर से प्रायोरिटी क्यू के अंदर इंसर्ट कर देंगे. Okay, so let's perform this step. This is what the priority queue we were having at step number 2. Then step number 3, what are we going to do is we will create a new node. We'll dequeue one time, so 1 and capital E becomes left child. We dequeue for second time, and 1 and small I becomes right child. Okay, then the number of occurrences, we are going to sum it up. So the new node will have frequency 1 plus 1 equals to 2. And this final tree, okay, this final tree with frequency 2, we are again going to enqueue in our priority queue. Insert करो. Now priority queue में जब आप insert करते हो तो it becomes still sorted. So ये नया node कहाँ पे जाएगा? It will be inserted at this place, 2 and 4 के बीच में, right? Because अगर equal priority है, equal frequency है, then first come first serve. लेकिन 4 से इसकी frequency कम है, so ये 4 से आगे रहेगा, and that's where you have that node here as a result. Fine. So दो बार dequeue करो, दोनों की फ्रीक्वेंसी का सम करके नया रूट बना लो. फाइनली उस ट्री को वापस अपने प्रायोरिटी क्यू के अंदर इंसर्ट करो. नाउ वी आर गोइंग टू रिपीट दिस स्टेप जब तक हमारे प्रायोरिटी क्यू के अंदर एक से ज्यादा नोड है, हम इसको रिपीट करते जाएंगे. ओके, सो इफ यू से दिस इज योर फाइनल रिजल्ट, okay, this is your final result at this place, then let us continue. This is the same thing. We have a final result after previous step. So again we are going to dequeue 2 times, 1 and Y, second 1 and L. We'll create a new node and we'll sum it up, the frequency. And if this is your final result, we are going to enqueue that at this place. So आगे से 1Y 1L निकल जाएंगे, लेकिन उसका एक नया ट्री बन के पीछे ऐड हो जाएगा. So when you perform this thing, this will be your result, 1Y 1L. Again you continue the same process. So dequeue 1 and small k, dequeue 1 and dot. create a new node, sum up the frequency, and having frequency 2, this will be inserted at this place. So you repeat this process. आप 2 and 2 को DQ करोगे, 4 will be inserted between 4 and 8. Again 2 and 2, 4 and 8. Then 2 and 2, 4 and 8 के बीच में चलता जाएगा. Then later on you'll have something 4 plus 4, 8, 8 plus 4, 12, and so on. So you continuously repeat this process, and at the end you will have this tree. When you have a single node in your priority queue, remember, when you have a single node in your priority queue, you will stop this process, and this will be your final Huffman tree. Yeah, okay, Sanjna, so you have any question? Either you can type or you can speak directly. Sanjna, you have raised your hand, so do you have any question? What? Okay then. So when you repeatedly do that process, this is what the final tree you will find. Look, calculating or creating a Huffman tree is very much simple one. Sort your characters based on the frequency in ascending order. Then DQ 2 times, sum up frequency, create a new node, and queue again. Repeat this process and you'll have this tree. So this was the step number 3, creating Huffman tree. Then step number 4 says that you traverse your entire tree and define code words. We traverse this tree and we will define code words. So the traversing process says that now this tree actually contains all the code words for your characters. Now how it defines, we will see. Now the frequency of root node will be the total number of characters in your entire message. That will be 26 characters in our entire message. So this 26 will be the root node frequency. That must happen, otherwise there might have gone something wrong. Okay, so this is a cross verification where we have done proper process or not. Fine. So the frequency of root node will be equals to what? Will be equals to the total number of characters in your entire message. That must happen. Now when we go and traverse this entire tree, what we'll do is, when we go left side, we will consider it as a bit 0, and when we go right side, we'll consider it as a bit 1. So 0 and 1. And considering these zeros and ones, we are going to define a code word. Now your code word will be completed when you reach at the leaf node. Fine. So that's how we define code words. Let's go and traverse this tree. So let me define those zeros and ones. So left side is 0, right side is 1. And always that happens. So 0 and 1, 0 and 1. So on every branch, I have written 0 and 1. Now, let's say starting from this root node, let us traverse and reach up to this capital E and find out what code word we have. So from that root node, if we want to reach up to capital E, we go to left side, so 1 0, we go to left side again, second 0. Third time we go to left side, so third 0. And fourth time also we go to left side, so fourth time 0. 0 0 0 0. Now that is the code word for capital E, and we'll list it in a table, right? So that was one example. Now let's say starting from root, we want to reach up to space. We want to reach up to space and find out what will be the code word for space. So to reach up to the space node, one time we go to left side, so 0. Then we go to right side, so 1. And then again we go to right side, 1. And we reach up to the leaf node space. So the code word for space is 0 1 1. Okay, that's what the code word for space is. Now if you want to find out the code word for small e, then let us traverse our tree and reach up to the small e node. We go to right side once, so 1. Then we go to left side, so 0 1 0. And that's the code word for your small e character. So likewise, you find out the code word for each and every character. Now here, if you carefully look at all the code words, then the character which was occurring more number of times has a code word with shorter length. स्मॉल ई सबसे ज्यादा अकर हो रहा था 8 बार, तो उसके कोडवर्ड की लेंथ शॉर्टर है, छोटा है. जो ज्यादा बार अकर होगा उसको मैं छोटा बनाऊंगा, सो दैट इट विल नॉट टेक मच स्पेस. और जो कम बार अकर हो रहा है, once or twice only, will have a longer code word because that doesn't matter, वो एक या दो बार ही आएगा तो ठीक है, चलेगा. So this is how we define all the code words. Now once we have those code words, then your step number 5. एक बार आपके पास अगर कोड वर्ड आ जाए तो आप क्या करोगे, आप फिर से अपना मैसेज स्कैन करके अपने कैरेक्टर्स को कोड वर्ड से रिप्लेस करोगे. So now we have our message and we are going to replace these characters with the code words we have. So the first character is capital E, and capital E has 4 times 0. So we are going to write 4 times 0 in place of capital E. Then we have small e. Small e has 1 0 code word, so we will write 1 0 here, and so on. Next is R. R has 1 1 0 0, so 1 1 0 0. Then you have I. Code word for I is 0 0 1, so then we have 0 0 1. Likewise, you replace all your characters with the code words, and finally this single sequence of bits, zeros and ones, you will have as a result. Okay, instead of your pure text message, your eyes seen near leg, you will have a sequence of zeros and ones as a final result. And this is your Huffman code. And to create this Huffman code, we have seen Huffman tree. And that Huffman tree is the best example of weight balanced tree. Now, why weight balanced tree? Because higher the weight, okay, you can see here, higher the weight will be nearer to the root node, and lower the weight will be much far compared to others, right? So all these are having lower weights. So that's how it says it's a weight balanced tree. Okay. Now, how this helps us? How this Huffman code helps us? Because when we started this example, we talked about why don't we simply transfer text message? Why we go for Huffman code? अगर अभी आप यहाँ पे देखोगे सिंपल टेक्स्ट मैसेज और 0 1 की जो सीक्वेंस है उसको, so by looking at this thing you will say that sir ये 0 1 की सीक्वेंस जो है वो तो काफी लंबी है, right? Now then how it is better than transferring the small message? Let's understand it. This is your final sequence of zeros and ones. Now, have we made anything better? So if you count all these bits, either zeros and ones, then this is actually having 73 bits. 73 bits. Now, if you have transferred your simple text message, then it was having 26 characters. Now, if you transfer those 26 characters, and each character requires 1 byte, so total 8 bit, then to transfer that entire text message you will require 208 bits. But instead of that, here we only need to transfer 73 bits. Zeros and ones are not characters. Remember, these zeros and ones are only bits, low and high. Okay. So transferring 73 bits instead of 208 bits is much smaller data transfer. And that's how it helps us. So you transfer this Huffman code to the other hand, and at the other hand again you traverse that tree. आपके पास जो Huffman tree है वो Huffman tree को ये bit के साथ 0101 के साथ left right traverse करते जाओ. When you reach at the leaf node आपको वो character मिल जाएगा. वापस character मिल गया, again ये traversal चालू रखो from the root. When you reach up to the leaf node आपको दूसरा character मिल जाएगा, and so on. So when you complete that traversal process with these 73 bits आपको पुराना message वापस मिलेगा. And this is what happens, or this is what is used in the fax transfer, fax machines. Fax machines are using this Huffman code to transfer the data, provided that whatever you have created Huffman tree, it must be available at both the ends. तो आपको Huffman tree पहले transfer कर देना पड़ेगा, and then you can transfer your message. Fine. But the Huffman tree, how many nodes it can have? अगर आपका simple message, text message है, which considers alphabets, numbers, and limited special characters, तो Huffman tree बहुत बड़ा नहीं होगा. It will be in a limited size, and that's why it is much better to go for it. Okay, so that's the Huffman code and Huffman tree we have seen. So whatever we have discussed, it is used to compress your data for the transmission. It is a statistical coding. Why statistical? Because what we consider is we consider the number of frequency of occurrence of the character. and those are the numbers. So it's a statistical coding. It works well for text and fax transmissions. Okay, and this is, we can say, this entire process, encoding and decoding process, is the application that covers multiple data structures. It covers tree, it covers priority queue, right? It covers set also. So this is one example which covers multiple data structures, and that's what the Huffman code is. So till now, what we have seen was we started with the tree definitions and representation of tree, binary tree traversals, binary search tree, general tree, threaded binary tree, some applications of tree we have seen, like family tree, tournament tree, expression tree. These were the topics we have covered. And then we moved towards the balanced trees, where we have seen height balanced tree and weight balanced tree. That completes our tree structure. Okay, so here we complete our tree. Next, we want to have a look at is the graph. Is the graph. Before we take break, let's have something related to graph also. So in a graph, we're going to start with the basic understanding of graph, what graph is, what are the terminologies used in a graph theory, how can we store our graph, okay, in a matrix structure or even in linked list form. And once we store the data structure, graph data structure, in a memory, then definitely we either need to traverse that graph data structure, and once we traverse, we might perform other operations. So first thing, how to traverse. So there are two different ways of traversal process: depth first search and the breadth first search, DFS and BFS. And once we know how to traverse, then we might need to extract few information from the graph. And definitely when we have a graph, we want to find out path, connectivity. So for that, for that path being minimum one and so on, we have different algorithms here. Minimum spanning tree we will see, and to find minimum spanning tree, we have two algorithms, Prince and Kruskal's algorithm. Then there is one more algorithm, Dijkstra, which is a single source shortest path. Okay, single source shortest path. And there is one last algorithm we need to have a look at in graph, which is Warshall algorithm, which is all pair shortest path. Now, to understand Warshall, we first need to understand what is path matrix. Fine. So that's what we are going to consider in a graph. Now, someone raised the hand. Anyone has any question? Any question till now? Now, this is the overview of graph section. These are the topics we are going to consider in graph. That's the second nonlinear data structure. Any question? Okay then. So let's continue with graph, and we'll consider a few terminologies related to graph, and then we'll take one break. Okay. Graph. Now, you might have gone through graphs in mathematics or even in your schooling part. So we are going to quickly consider these basic terminologies of graph. Graph G is nothing but a set of V and E. V for set of vertices, finite set of vertices, and capital E is a finite set of edges. Edge. And edge is nothing but the ordered pair of your two vertices. Ordered pair, remember. Now, there can be two different uh, types of graphs: undirected graph and directed graph. If your edges does have a direction like this way, if your edges does have a direction, then it is a directed graph. Otherwise, it is undirected graph. Now, in undirected graph, you can consider connectivity in both the directions, to and fro. But in directed graph, you can consider the direction only in the direction of your arrow, A to B. You cannot say that B to A, there is an edge. And that's why edge is always a ordered pair of two vertices. So we can have either directed graph or undirected graph. Now we have seen directed and undirected graphs. There are a few more types of graphs, so let's go through each type here. If you have undirected graph, then edge UV and edge VU both will be equal because there is no direction. But that will not happen in directed graph. Now this is for all VV belongs to capital E. Capital E is a set of edges. Okay. And remember, there is no self loop in undirected graph. Now in your directed graph, edge UV is what? It is actually the edge from U to V. U to V. That's your edge. And in reverse direction, it is not true. Self loops are allowed here. So that's directed graph. Now we might have weighted graph also. So each edge has some weight associated with it. Okay. So that weight is a function from E to R actually. Edge have some weight, rational number. So weight W is a function from E to R. So I can say that from A to B, I have an edge with weight, let's say 20. Now this weight can be anything depending on your application. If you are creating a graph for roadways, then it can be kilometer. Okay. If you are creating a graph for airways, then it can be the air distance. If you are creating a graph for computer network, then the edge weight can be the number of hop, or it can be the cost to traverse that path, right? So depending on your application, edge weight can be anything, whatever is required. So that is a weighted graph. Then you might have dense graph or a sparse graph. So if you are having maximum more number of edges in your graph, then it can be dense graph. And if you have very less number of edges in your graph, then it can be the sparse graph. So modulo of capital E is almost equal to modulo of V square. Then it will be dense. And if modulo of E is much lesser than V square, then it is sparse. So these are few types of graphs: undirected graph, directed graph, weighted graph, dense graph, sparse graph. Then let's have few terminologies here related to graph. So adjacent node. Now, when you say two vertices are adjacent, if you have an edge in between those two nodes, if those two nodes are endpoints of single edge, same edge, then those two vertices are adjacent to each other. एक एज अगर आप कंसिडर करो तो उसके दोनों साइड जो नोड हैं वो दोनों एक दूसरे के एडजेसेंट नोड कहलाएंगे. In other words, we can say edge is incident to a vertex. तो दो वर्टेक्स के बीच का रिलेशन एडजेसेंट हुआ, वर्टेक्स और एज के बीच का रिलेशन क्या होगा? इंसिडेंट. इफ दैट वर्टेक्स इज द एंड पॉइंट ऑफ दैट एज, तो एज इंसिडेंट है, ये बोलेंगे. देन आउटगोइंग एज, इनकमिंग एज. If you have a direction in your edge, then you can easily define which is outgoing edge and which is incoming edge. अगर वो वर्टेक्स से origin होगी तो outgoing, अगर वो वर्टेक्स as a destination होगी then it is incoming. Then degree of vertex. Vertex is a node. Okay, so degree of vertex denoted by dag of v is actually the number of incident edges. Look, incident edge doesn't matter whether it is incoming or outgoing. जो भी है total मारो, that will be the degree of vertex. अगर आप ये दोनों को incoming, outgoing दोनों को अलग रखते हो, then you can say out degree and in degree. So the number of outgoing edges will be the out degree of vertex v, and the number of incoming edges will be the in degree of that vertex. And the normal degree of vertex will be the total of these two. So these are few terminologies related to graph: adjacent nodes, outgoing edge, incoming edge, degree of a vertex, incident edge. You should read these definitions carefully, because these can be asked in a 1-mark question. What do you mean by incident node? What is incoming edge? What is degree of a vertex? Short question. Okay, short answer question. And these are very much simple ones. So with reading it one time only, carefully reading it once, you can remember these things. These are very much simple one. Then the path. What is a path? So path is nothing but a sequence of vertices. एक सोर्स वर्टेक्स से आप डेस्टिनेशन वर्टेक्स तक ग्राफ को जब ट्रैवर्स करोगे तो आपको एक पाथ मिलेगा. नाउ पाथ कैन बी डिफाइंड as a sequence of vertices such that vertex is adjacent to the next vertex. एक वर्टेक्स से दूसरे वर्टेक्स पे जाओगे, दूसरे से थर्ड वर्टेक्स, थर्ड से फोर्थ वर्टेक्स, एंड लेट्स से फोर्थ वर्टेक्स इज योर डेस्टिनेशन. So ये जो sequence है, sequence of vertices will be considered as a graph. Each edge can be traveled only once. ये याद रखना है. When we say a path, each edge in your entire path must be traversed once only. वो repeat नहीं होनी चाहिए, otherwise ये होगा कि आपने बीच में कहीं पे loop बना दी. So there must not be any loop, any cycle in a path. Now, once you have that path, length of the path will be the number of edges that you have traversed. Number of edges that you traverse will be the length of your path. Now, if there is a cyclic path, then it is called cycle or a loop. It is nothing but a path that starts and ends at the same vertex. घूम के वापस same vertex पे आ जाओ, then you found a loop, you found a cycle. And in weighted graph, अगर आपके पास हर एक edge का weight है, then every edge is assigned some weight that can be either kilometers in terms of length. So length of a path, the number of edges, and total cost of that path will be the total length or total weight of each and every edge. Right? So these are a few more terminologies related to graph. Now, adjacency relationship and how we can define this adjacency matrix and adjacency list to store our graph in a memory. We'll see that after a few minutes break. So let's take a break here. 5 minutes break, and you can be here in the same meeting. We are going to start our next session at 10:30 again. Thank you for being here. You can take your break, freshen up, and with fresh mind, we are going to start our next topic after 5 minutes. During that 5 minutes, if you have any question, you can ask.